Okay. So last time I defined for you the Bruhat order, and the plan for today is to start proving some properties of this Bruhat order. Okay. Now, as I told you, you remember that we spent the first 2 weeks of the class developing this theory of the sign permutation representation. But the main purpose of developing that theory was to prove the exchange property and the deletion property. Okay? And so these are the two things that we're going to use to prove everything about the Bruhat order. So I want to make sure that you are comfortable with these two things. So exchange. So this is going to be like in the newspaper where you have two pictures and you have to find the difference. So this is a little bit different from the exchange property of last time, and your job is to tell me why it's different. So exchange, if W is S1 up to Sk, and if you multiply W by a reflection T, and you get something shorter, that means that when you multiply W by the reflection T, you can obtain that by just removing one of the SI's in this word. And this also gives you a description of which are the reflections T that shorten W. They are all of the form Sk down to Si up to Sk. So what's the difference? Last time, I wrote TW. So last time I was considering multiplication by T on the left. This time I'm considering multiplication by T on the right. But last time TW was just what you would see here, and last time T was S1 up to Si down to S1. Okay. So this is basically the same exchange property. The only difference is that now I want to understand when multiplying on the right makes me become shorter. The proof is exactly the same as the other exchange property. And deletion. It says if we have a word for W and this word is not reduced, then we can reduce it by eliminating two of the letters in that word. Okay? So we're going to use these two things to prove properties of the Bruhat order. Okay. Before I do that, let me remind you how I define the Bruhat order and remind myself. So we said that you have an arrow from U to V if V is equal to UT and the length of V is bigger than the length of U for some T in T. So what we said is that you have an arrow when you take something and you multiply it on the right by a reflection, making it bigger, making it have a longer length. And because I'm multiplying by T on the right here, that's why I want an exchange property that explains to me what happens when I multiply on the right. So I proved it on the left, but the same thing is true for the right side. So this is how we defined the arrows of the Bruhat graph. And then I said U is less than V in the Bruhat order. Basically, if there is a path in the Bruhat graph. So U is W0, which goes to W1, etc. WK equal to V. For some W0 up to WK in W. Okay? So if I want to move up in the Bruhat order, I have to take some guy U and then start multiplying by reflections on the right, each time making it longer. That's what it means to be bigger in the Bruhat order. Okay? Any questions about this? Actually, let me give you a good exercise. if I made this definition, but instead of writing v equals ut, I wrote v equals tu, I would get an equivalent thing. So u is directed to v if and only if I can write v as t prime u for some t prime in t and length of v bigger than length of u. Okay? What's the point of this? The point is that seeing this definition, you might think that the Bruhat order somehow cares about the right side, multiplying on the right side. But this tells me that actually it doesn't care, because if you can get something by multiplying by reflection on the right, then you can also get it by multiplying by reflection on the left. It's an easy exercise, and you should do it. And what that means is that if I take my Bruhat order, if I take an element u and I start multiplying by things on the right, on the left, on the right, on the right, on the left, as long as I become longer each time, I'm going up in the Bruhat order. Okay? So that was the definition. But this definition is a little bit hard to work with, because if I give you two words, how do you tell if one is bigger than the other one? You have to find a path, and that might not be very easy. So the first thing that I want to do today is give you a simpler description of the Bruhat order. So this is the theorem, first theorem I want to prove today, called the subword property. It gives me a simpler way of understanding the Bruhat order. Let's say that V can be written in a reduced way like this. Be a reduced word for V. Okay? Then U is less than or equal to V if and only if U is a subword of this word. So U can be written in the form SI1, SI2, up until SIK for some subindices. Okay? So if you want to know which are all the elements of the Coxeter group that are less than this one, you just have to take an ordered subword. Take a letter, take a letter, take a letter, and that's less than V, and nothing else is less than V. Okay? So I'm going to call this U, well, I call this a subword of S1 up to SQ. You just read from left to right and choose some of the letters, and you don't choose the other ones. Okay? Is that good? Any questions? Now, sometimes there's two ways of stating this. The first way of stating this is U is less than V if and only if U can be written as a subword. Another equivalent way of stating it, No. No, so that's a very good question. The question is, do these letters have to be consecutive? No. So, for example, you might have A, B, F, B, A, C, D, and a subword of this is A, B, D. So A, B, D is less than this. There's a subword of this, let's say. Subword of this. Now, I can equivalently say, if and only if u equals the same thing. But I can assume that this is a reduced word. For u, for some 1 less than or equal to I1, etc. Ik less than or equal to q. So why are these two equivalent? Because if you have a reduced word that is a subword, then that's a word. Now, if you have a word, then we know that every word contains a reduced word as a subword. In other words, if u can be written in this way, and this is not a reduced expression, then I can reduce it by taking out two things at a time, and by the deletion property. And by doing that, I obtain a reduced expression that is also a subword. So you can feel free to either include or not include reduced in this theorem, and it's true in any case. Okay. Any questions about this statement of the theorem? Okay. I think we're going to spend most of the time proving this. So let's go first in this direction. Let's assume that u is less than v, and let's prove that u can be written as a subword of the word of v. Okay? So first I'm going to prove it for when I have an arrow from u to v. So first I'm going to prove if there's an arrow from u to v, then u is a subword of v. So what does this mean? I have an arrow that means that v is equal to u times t, where the length of v is bigger than the length of u for some t, a reflection. Okay? Now what I want to do is say, okay, I want to use these two things. What I told you is that these are the two properties that I'm going to keep using the whole time. So here I am almost in this situation, except that the inequality is the opposite, right? Here L of ut is bigger than u, and there it's smaller. So what I'm going to do is just say, remember that t is a reflection, and reflection squared equal the identity. So that means that I can write this as v and the vt. What did I do here? I'm claiming that u is equal to vt. And why is that? Because vt is equal to, v is ut, so utt. But remember that all the reflections have order 2. Do you remember that? We haven't talked about that in a while, but it's true. And proving it is very easy. T squared is the identity, so this is u. Okay? And now I am in that situation. So I can say that vt can be written as, v is given by s1 up to sq, and so vt can be written as s1 ... then I get rid of si, sq. Yeah? And vt is u. Is that okay? So I assume that u is greater, u has an arrow to v, and I prove that u has this expression, which is a subword of the word of v. Subword of the one for v. So that proves that direction. Well, that proves it for u arrow v. Okay. Any questions about that so far? Pregunta? No? ¿Seguro? So que U era menor que B. So the question is where we use that U is shorter than V, and we used it here, except that we took U and wrote it as VT. And we wrote the same condition in a way that we can use the exchange property. Okay, so this proves it for when I have an arrow from U to V, and now if I have U is less than or equal to V, then that means that I have a sequence of arrows from U to V, and I can apply what I just said, right? Here I have some V, then whenever I have an arrow, that means that this guy is a subword of this one. So WK minus 1 is a subword of V, WK minus 2 is a subword of WK minus 1, so it's a subword of V, and so by induction, W0 is a subword of V. So U can be written as a subword of V. Is that okay? So that proves the first direction. Now, let's prove the other direction. So let's assume, basically what I have to do is show that every subword of a reduced word is smaller than it in the Bruhat order. Okay? And the way I'm going to do this is I'm going to do it by induction on the difference of length between V and U. Okay? So I'm going to induct on the length of V minus the length of U. So first let's assume that that difference is 1. Okay? So V equals S1 up to SQ is reduced. U is supposed to be a subword of it, but V has length Q, so U has length Q minus 1. So that reduced word must be obtained by removing only one letter. Let's say that it's I. Okay? And this must be reduced. And now what I want to say is that because of what I said here, that whenever I want, I can assume that these words are reduced because it's equivalent that I have a subword or that I have a reduced subword. Now the thing is that this guy is reduced, so the length of V is Q, and the difference is 1, so the length of U is Q minus 1. So if I take a subword of this one, and this guy has length Q minus 1, then it must be that I'm using exactly Q minus 1 letters, and it must be that this word is reduced. Okay? Now, what am I trying to prove? I'm trying to prove that U is less than or equal to V in the Bruhat order, but hopefully I can prove that actually there's an arrow between U and V. Now, I think I can do that because this looks basically like this, right? Actually, if you remember, I should have said this, that this is not only an if, this is an if and only if. But so if I assume this, then I get this also. Another way of saying it is just that I can write this as S1 dot 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 SQ SQ dot 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 SI dot 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 SQ. So So let's take a second to understand what I just wrote. I'm just saying that U can be rewritten in this way. Okay? Let me make a little bit more space here. So Si is 1. So I claim that these two things are equal. Why? Because what I'm doing is, when I multiply all of this out, you see this thing and this thing are inverses of each other. Yeah, because they're the reverse of each other. So when I multiply this by this, I'm going to get S1 up to Si minus 1, then Si plus 1 up to SQ. So these two things are equal to each other. Okay? Why do I do this? The reason I do this is because I now would like to say that this is V. And what can you tell me about this thing right here? Well, it's a reflection because it's palindromic. Remember that the reflections are exactly the things that are palindromic. So this is a reflection in T. So what did I do? I wrote U as V times T, where U is shorter than V. And that's exactly the definition of having an arrow from U to V. Okay? Uh-huh.
Why did you need the even only?
I basically just wanted to say that if I didn't really use it. I proved it here, basically. What I was trying to say is that once I know that U is of this form, then I wanted to say it's of the form W times a reflection. And that's what I proved here. So that you don't have to trust me that it's an if and only if. This is the proof. Okay. So that proves the initial case. Not bad. Now I have to prove the induction. So it's going to take some space, so maybe I should move somewhere else. Well, let's start here. So now let's assume that L of V minus L of U is equal to K. And I would like to make some kind of inductive argument. Now, the mental picture you should have in mind is basically that my Bruhat order goes from shorter words to longer words. V is up here, U is down here, and the difference of length is K. I want to do an induction. And so to do an induction, I want to just find something in between that I can apply induction to. Okay? So my plan is going to be to find something here so that I can just inductively say, I want to apply my induction hypothesis here and my induction hypothesis here. That's my plan. So let's do that. V is equal to S1 up to SQ, reduced. And I'm assuming that I have a reduced subword for U in there. So that must be obtained by taking this thing, and because the difference in lengths is K, that means I have to take out K of the things. So I take, let's say, A1 out, I take A2 out, I take AK out, and that's it. And this is reduced. Okay? Now, there may be different ways of doing this, right? Because all I know is that U is a subword of this, but there may be different subwords that give me the same answer U. So there may be different choices of the AIs. Okay? And what I want to do, and you will see later why I want to do this, I want to choose this so that AK is the largest possible. Okay? So out of all the possible subwords for U, I'm going to choose one where A sub K is maximum. Okay? And you'll see why I do that. Now, what I want to do is tell you what t I'm going to multiply by. Okay? So the t that I'm going to multiply by, I'll tell you right here, is I want to get something longer. So what I want to do is basically I want to put the AK back here. So I want to multiply by SQ dot 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 S sub AK and up to SQ. So this is a palindromic word. I start with SQ, I go down to AK, and I go up to SQ. Okay? Now, when you go ahead and multiply this, you get what? Let's go and do it back here. When I multiply u times t, then all of these guys between AK plus 1 and q are going to cancel all of these guys between q and AK plus 1. And then these guys are going to reappear, which are going to take the spot of everything like this. Okay? So when you carry out this multiplication, the only thing that happens is that you put S sub AK back in here. Okay. So UT is just the same thing except that I put S sub AK back. Okay. And I don't know, is this longer or shorter than U? It looks longer, but we don't know if it's reduced. Okay? So we have to be a little bit careful. It looks longer, it has one more letter, but it could be that this is reducible. Okay? So there's two cases. The first case is that, well, let me write them here. L of U. Remember, when I multiply by t, I said that either the length goes up by 1 or down by 1. Yeah? Is that true? No, that's not true. That's not true. Let's say so when I multiply this, it either became longer or shorter. So first, let's assume that it became longer. Then I can make the argument that I would like to make, which is the following. I say, here's V, here's U, here's UT, okay? L of U plus 1, right? This thing has length L of U plus 1. Okay? So if UT is longer than L of U, it cannot be longer than L of U plus 1 because here's an expression of length L of U plus 1. So if it's bigger, then it has to be exactly equal to L of U plus 1. And then I want to say the following. I want to say, well, look, UT is a subword of V. Yeah? Look at it. UT, subword of V. And U is a subword of UT, right? because U is obtained from UT by just removing S sub AK. And the lengths are shorter. I mean, the difference in length is shorter. Yeah? Because here the difference in length is L of U minus 1, and here it's 1. So I can apply my induction hypothesis. Okay? So by induction, I obtain that UT is really less than or equal to V in the Bruhat order, that U is less than or equal to U of the UT in the Bruhat order, and posits are transitive, so U is less than or equal to V. Okay? So this is basically the argument that I want to make, and if you look at it, I really haven't done anything clever here. I just did an induction, and it's the first thing that you try works. The problem is that there's another case. And what I would like to do now is prove to you that this case is not going to happen. Okay? So case 2 is that L of UT is less than L of U. By the way, let me ask you something. Why is it that L of UT cannot equal L of U? I haven't justified that. Any ideas? Parity. So luckily there's an easy argument, which is that T is odd. Yeah? All reflections are odd. And so this thing has one parity and this thing has a different parity, so they cannot be equal. So that's lucky. We didn't have to think very hard to deal with that case. Now L of UT is less than L of U. We like that, right? Because that's exactly when we can apply exchange. Okay? So let's apply exchange. But let me remind you, so what is U? U is S1, then SA1 is missing, SAK is missing, and then SQ. So by exchange, I know that UT can be obtained by removing a single letter from here. Yeah? But actually, I don't care about that. I care more about the other one. UT is something, but what I care about is what T is. The second part of the exchange property, which tells me that T can be obtained by starting at the end of the word, going down up to some point, and returning to the end of the word. Okay? So, because L of UT is less than U, that means that T can be obtained by starting at the end of the word, then going down somewhere and returning up to the end of the word. There's two cases. The first case is that I go past AK and back up. Second case is that I don't reach AK like this. Okay? So let's do the two cases. The first case is that I went down to SI and up to SQ, and I didn't reach AK. Okay? Or the second case is that I did reach it, okay? Then I went down to some SI and then back up, and I did reach AK and Q. 4, I less than AK. Now, I'm not saying that I only crossed AK. It could be that I crossed AK minus 1 up to some point. The only thing that I'm conditioning on is whether I crossed the last one or I didn't cross the last one. These are my two cases, case A or case B. And let me prove to you that case A cannot happen, case B cannot happen. So, how do I prove that case A cannot happen? I do it in the following way. Let me just make a computation here. V is equal to, I mean, what's the point? The point is that I have an expression for T, and I have a different expression for T. And in an exercise in the forum, you prove that this can't happen. Okay. But if you didn't look at the forum, how do you prove that you cannot have two different expressions for T of this form? Well, let's do it. So this is what I forget if someone actually wrote this on the forum or not, but one way of proving it is like this. V is equal to VTT. Okay? What's V? V is S1 up to SQ. What's T? Let me plug in T equal to that one first. T is equal to SQ down to AK and up to Q. So this is V, this is T. And then for the second T, let me plug in this second expression. What does this do? You've noticed by now what happens when we multiply by something like this. This SQ up to SAK cancels this SQ up to SAK. And then I start at SAK plus 1. So what that does is that it just removes the occurrence of AK in this word. And what this does is that it removes the occurrence of SI. So if you do this carefully, what you get is S1, then you see that AK is missing, then you see that SI is missing, and then you get to SQ. Okay? And this is a contradiction because I assumed that V had length Q. Okay? I assumed that that was a reduced word for V, and this one is shorter. Contradiction. Okay. This is kind of a slick proof, but if you try to prove it, you're either going to find this proof or a different proof for why you can't have two expressions for T that look like this. So that deals with case A. Finally, we need to deal with case B. Okay. So let's do case B. So, case B. Again, the same thing works. The same idea works, which is that here I have one expression for T, and there I have a different expression for T. And I'm going to do basically the same argument, but maybe it's instructive for you to try to make this argument in case B, and you'll see that it doesn't really conclude. I have to make a slightly different argument, which is just to say U is equal to UTT. Okay. So I'm going to do the same thing, but with U instead of B. So let's do this. U, I know what that is 1 up to SA1 is missing, SAK is missing, I get to SQ, so that's U. And then I'm going to substitute for T twice, once with this expression and once with that expression. Let me first introduce this one. So this gives me SQ, then I go down to SAK, then I'm down to SI, then up to SAK, and up to SQ. So this is U, this is T. And then let me multiply by this expression for T. Okay. And let's see what this does. Well, again, it's basically the same thing. That what happens when I multiply by this thing, by SQ down to SI up to SQ. Again, this is going to cancel out with this, where this is I here. Okay. And then I'm going to start at SI plus 1. So the effect of multiplying these two things together is just removing SI. So let me just write it like this, S1, SA1, then I remove SI, then I remove AK, and then Q. So this is U times T. And I multiply by SQ down to AK and up to SQ. Okay. What happens when I multiply these two things together now? Well, again, it's almost the same thing. From AK plus 1 up to SQ, it's going to cancel all of these things. And then it's going to put this back together. So what it's doing is that it's adding SAK. Okay. S1. So you notice now basically what happens when I multiply by things like this, either they add AK or they remove AK. That's what's been happening this whole time. And what I did is that I got an expression like this. Why is this a problem? It's not a problem because I made a mistake. It's not a problem because I made a mistake here. I didn't mean to say max, I meant to say min. I wanted to take a word for which the largest missing letter was as small as possible. AK was as small as possible. What I did here is that I found a different word for U. What length does it have? It has the same length because it's just missing SI and it's including SAK. And now the first missing letter is further to the left, which contradicts my choice. I is less than. So the first missing, the last missing letter is less than AK, which contradicts my choice that AK was minimum with this property. Okay? And this gives me a contradiction. Okay? So that's it, right? I'm done. Maybe we should step back and see what we did. So what is it that we did? I said this. I basically split it into two cases, where case 1 was the case that I believed to be true. We all believed that this was reduced. Okay. If it is reduced, then we made the argument inductively. And if it's not reduced, we found contradictions. Okay, and it took us a little bit of work, but we found. And that proves this theorem that the Bruhat order is just describing containment of words. It's a much simpler description than that inductive description by walking up in the graph. Any questions?
possible that I is bigger or smaller than AK?
Was the answer right here? Did I just erase it? Where do
No.
oh no, there. Because AK is not in this word. So you either go to here or to here, but you can't choose this one because it's not in the word. So summary, U is less than or equal to V if U is a subword of, or U can be written. Have to be a little bit careful there. If and only if U can be written as a subword of a reduced word for V. Do you know this? Si saben, esto es como sí, solo sí. Igual. That's it. It's a good description. Let me show you a good corollary of this. Very nice corollary. U is less than or equal to V if and only if U inverse is less than or equal to V inverse. Why is that? That might have seemed hard before, but now we get it for free because we know that the word for U inverse is just the reversal of the word for U. So if V is a subword of U, then the reverse of V is a subword of the reverse of U. So you get this for free. Proof. There's nothing to say here. That. Easy. So that's a nice consequence. Let me show you another nice consequence. Another nice consequence is this one, corollary. And this sometimes is called the chain property. It says if U is less than V, and let's say that the length of V minus the length of U is K, then I can get from U to V by a sequence of exactly length K. U is less than, let's say U is equal to V0, less than V1, less than V2, less than Vk, which is U. Where this one has, so what are the lengths here? This one has length U, length of U plus 1, length of U plus 2, up until length of U plus K. Why is this true? Again, this is free now, because I'm saying I have V. Now I get to U by removing K letters. So let me just remove them one at a time. Okay, and I get my sequence. Remove one letter and I get Bk minus 1. Remove another one and I get Bk minus 2. And so I get them like that. What is this saying? So again, proof. It's just kind of thinking about why we proved it already. But why is this very important? Because if you remember we only drew one Bruhat order so far. It looked like this. This is the Bruhat order for S3. It's a very nice poset in that it has levels. This is what's called a graded poset. What's an example of a poset that is not graded? Something like this. Okay. Here I have a very well-defined notion of height. Height 0, height 1, height 2, height 3. But here I don't, because if I define this to be height 0, then these two should be height 1, then this one should be height 2, and now should I say this is height 2 or height 3? This is called not graded. But what this corollary tells me is that I'm never going to see something like this. Because if the difference between this one and this one is length 3, then there must be somewhere in between another word that I can add here. Okay? So what am I saying? Definition: a poset is graded if all chains from U to V, all maximal chains from U to V have the same length. And a chain is just moving up in the poset. Okay? So this is not graded because here's a maximal chain of length 2 and a maximal chain of length 3. And so the corollary of this, and a very important one, is that the Bruhat order is graded. And what is the, how do I know what the level of a word is? It's just the length, right? These ones have length 0, length 1, length 2, and so on. So it's graded by length. Okay. It's very good news, and it's not at all obvious news, but it's true. Okay. I think we should stop there. ¿Preguntas? ¿Alguna pregunta? Chain. ¿Está el video corriendo todavía? Let's answer in English. They're going to have the same question. A chain in a poset is a sequence of elements such that each one is less than the next one. So a chain is just a walk up in the poset. And maximal means that you cannot add anything to the chain. So for example, a chain that is not maximal is from here to here to here. That's not maximal because I could add from here, I could add this one. Okay. So basically what this is saying is, if you walk from U to V and you don't skip any steps, then you're never going to have a path of length 2, a path of length 3. ¿Más preguntas? Bueno, paremos entonces el video. Aquí estoy.